there already. Hello. Turn to page 543, and we're going to talk about the mid-chapter review here. So we've done 8.1 to 8.3. This is an official, just kind of a reminder of what we've learned and what you should be prepared for a quiz coming up. It says this: how can you estimate the measure of an angle given radians using degree measure and vice versa? So we talked early in the chapter about the connection between degrees and radians. First of all, radians is a different unit to measure angle measure. Okay, if you've ever really thought about 360 degrees, where does that even come from as far as, you know, one full time around a circle, right? One large angle, that's one complete time around the circle. Why is it 360? Why is it not 100? Why is it not 10? Why is it not 2? I don't know. So why do they divide it into 360 parts? Well, there is actually a little bit of a better reason for why they use the unit radians, and that is because the unit radians is based on pi, which is a natural innate characteristic of perfect circles. And so because we're talking about angle measures that open up like this, and really if you track an angle all the way around, it makes a complete circle, right? So angles are kind of associated with arcs, and if you take them all the way around, it's associated with a complete circle. So having said that, we talked about estimations, okay? We're not using pi in the initial explanation here, but if you wanted to estimate, let's say, for example, you want to estimate, 180, if you remember, 180 degrees is 1 pi radians, or 3.14, okay? That's the number of radians that 180 degrees is. So 360 degrees would be about 6.28, or 2 pi radians, okay? So this is the exact connection right here, and these are the estimations. So 1 radian is about 57.3 degrees is 1 radian, okay? Nothing to do with pi. That's why without pi, you see it's a pretty crazy decimal number. But right around, okay, where are we? Oh, I see. This is, okay, so this is starting from the top, like at a clock here. So just under 60 would be 1 radian here, okay? There's no real units on radians. When you see in the text, they don't have a unit like degrees or anything like that. It's just blank, but sometimes I put a little capital R there to signify radians, or RAD on your calculator, you'll see. So 1 radian is just under 60 degrees. If they ask you to estimate without using a calculator, you would kind of say, okay, 1 radian is about 60 degrees, maybe a little under. So if you were to estimate 210 degree angle, how many radians would that be? You'd probably say, well, let's see, here's about 3 radians, right? 180 is about 3.1 radians. And then 270 is, you know, a little bit more than that. So here's maybe 60, okay? And then here's like maybe half of 60. So 210, sorry, not 270, 210. 180 plus 30, which would be about a half a radian. So if you did 1, 2, 3.5, that would be a rough estimate. It's a little bit low, but it would be a rough estimate. Now we did talk about something a little more exact, right? And that was this: 180 degrees is to pi radians, just like any other degree measure would be to any other radian measure. So you could actually be a little bit more exact here for 210, and how you would do that is you would replace this degree part with 210. So you have degrees on top and radians on the bottom, and then you would solve for this right here, okay? You would solve for that. So you'd multiply, cross multiply and divide, and to get radian by itself. So the radians would go up here, this pi would go up here, so that's 210 pi times pi, and then the radians you would divide down here, so over 180, and that would be your radian measure. And that's exact. So we guessed about 3.5, but if we actually got our calculator out and used our simple proportion that I'm encouraging you to use there as well, let me just get out of here. So 210 times pi divided by 180 is 3.66, okay, or 3.67. So 3.5, rough estimate. This would be a little bit more exact, okay? Now, because we're rounding a decimal, it's still approximate, but that's the connection between radians and degrees. And I would strongly encourage you to try to remember this right here, 180 over pi equals degrees over radians. And then you can manipulate this simple proportion to solve either for radians or degrees, given one or the other. Okay, so here's a little bit more on estimating. Okay, let's move on to sine and cos now. So we talked about sine and cos as well. We called them sinusoidal functions, right? So anything that resembles a sine function kind of goes up and down like this regularly. That's called a sinusoidal function. So sine and cos have the same appearance. They have a lot of the same qualities, characteristics, such as the amplitude. So you'll remember that amplitude would be half of the distance from the max to the min. So here's the distance from the max to the min, and half of that is the amplitude here. Or from what we call the midline to the maximum displacement, or the midline to the minimum displacement there. So that's what amplitude is, and they both have the same amplitude of 1. Okay, amplitude is 1. They also have the same midline, that's y equals 0. That's the x-axis. The period is 2 pi, or 360 degrees. And how do you determine the period? Well, that's one complete cycle, right? So if you looked at the sine graph here, it goes up, and it goes down, it goes back up, and then it starts all over again. So that's one complete cycle, 360 degrees. Here's cosine, goes down to a minimum, goes up, back to a maximum. There's one complete cycle. That's 360 degree span as well. And that's why it's so commonly associated with the circle. Okay? Because after that, it just keeps repeating. It just keeps going over and over and over again. Over and over and over. Just stop me if you have any questions. I'm just going to keep rolling through this because it's review. But stop me if you have any questions. Okay. The maximum and minimum values are also +1 and -1 for sine and cos graphs. Okay. Domain is XER. That means there's no restrictions on the x variables there, no restrictions at all. And the range obviously only goes from -1 as a minimum to +1 as a maximum. That's for both. Okay. The graphs themselves, if you think about the sine and cos, they are the exact same shape. And actually, the cos graph and the sine graph are really mirrors of each other. They're just shifted a bit. So if I start back here at -90 degrees for the cos, and I just map this part of the cos graph, do you see how that's exactly the same as the sine graph? They just start at different spots. So they're very, very similar. The cos graph is just a sine graph that's shifted. And so it kind of looks like this. Right? That's the cos graph here, cos x. So it's the same, it's just shifted over a little bit. All right. How can we determine some of these characteristics? The amplitude is half of the vertical distance between max and min. We talked about that. So amplitude here is max minus min divided by 2. Yeah, so in this case, you'd have max would be 1 minus -1 over 2. So that's actually 1 plus 1. That's 2 over 2. That's 1. The amplitude is 1 unit, and that's what we see there. The equation of the midline is a little bit different. It's very similar, but it's a plus. So the equation of what this middle line is, and that's the one that kind of the horizontal line that goes right in the middle of the wave there, of the graph. So it's max plus min divided by 2. So it would be 1 plus -1 divided by 2, which is 0 over 2, or 0. So that's why we have y equals 0. Okay, the period, if we're finding out what the period is, that is the horizontal distance between any of the corresponding, 2 consecutive corresponding parts of the graph. So for example, you can use the crest here, crest to crest. those two consecutive corresponding parts of the graph. So the period for this sine graph, and it's also called a wave, right? In science, we talked a lot about waves, so we call it like a sine wave too. From 2 to 4, right? So the period length is 2 units here. It goes from 2 to 4, and then it repeats again. And you can use any spot that you know of. For example, you can go from here, which is 0.5, to the next one corresponding would be this one, right? Because they're on the down parts there. So here to 2.5 is still 2. From here, 1 to 3 is 2 units. So any of these corresponding parts of the graph, that's how you can calculate the period length. All right. If you're given the midline and the amplitude, you can always find the maximum value. That's another important thing. Without the graph, if you have the midline and the amplitude, you take the midline and you add the amplitude, and that's your max. Midline, subtract the amplitude, that's your minimum. And usually on the amplitude, there's no positive or negative. It's just, there's no sign on it. So it's just a magnitude. Okay, I think that is everything for 8.1 to 8.3. Is there anything that you've noticed that we've missed there from 8.1 to 8.3? Or might anybody have any questions about anything that we talked about here? Anybody? No? You're good? Okay, let me just double check here. So your mid-unit review from your textbook there. Of course, the textbook we're using is Nelson, Foundations of Math 12. And that's going to be on page 545 in your textbook there. So these are some of the questions here. Your mid-unit review.